Right now, as you are reading these lines, there is a truth that very few people on Earth have ever heard told. On the morning of the 21st of July, 2023, a NASA engineer sent a wrong command sequence. That command sequence flew at the speed of light for 18.5 hours, traveling 20 billion kilometers through space, and reached a 22-watt machine drifting silently at the edge of the solar system. The machine obeyed the command. It turned its antenna exactly 2 degrees away from Earth, just 2 degrees in a room small enough that you would not notice it. But at a distance of 20 billion kilometers, 2 degrees was enough to completely cut off all communication. And for the 12 days after that, no one on Earth knew for sure whether we would ever hear from it again. This was not a story about a new spacecraft. This machine was built before the internet existed, before home computers existed, before most of the scientists studying its data were even born. It was only designed to last 5 years. By 2023, it was 46 years old. It ran on 22 watts of electricity, the same as a light switch in a child's bedroom. And that tiny ancient machine held in its memory a set of data that no other machine in human history had ever collected. That is the story of Voyager 2. And this is the part that the headlines did not tell you. Not only did NASA almost lose it during those 12 days of silence, and the way they saved it was a technical gamble that even the project manager admitted had a very low chance of success. What Voyager 2 had measured 5 years before that incident, when it crossed the invisible edge of the solar system, did not match any scientific model that humanity had ever built. The researchers did not use words like interesting or surprising. They used words like cliff leak, unexplainable. And that data is now dividing the scientific community over a question that seems almost absurd. What is the real shape of our cosmic home? That is what is happening with this machine right now, as its last remaining senses are being turned off. And that is a moment in history that has been locked in, and will arrive in 2 years, the moment when a new mission will deliver the final answer. Stay with me, because by the time this story ends, you will never look at the night sky the same way again. I am Jack, this is Cosmic Proof. Subscribe right now, because tonight we are going to the edge of everything. Before we go on, let me quickly tell you who this machine really is. Its name is Voyager 2. It was launched on the 20th of August, 1977, 16 days before its twin Voyager 1. It was designed to last 5 years and visit 2 planets. 48 years later, it is still alive, and to this day it remains the only machine in human history to have visited all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. But the most important detail about Voyager 2 is not the 4 planets it visited. It is the path it took after its Neptune encounter in 1989, the path that led it to the event we just talked about, and is also the reason why only one single antenna on Earth could save it. The story of that path began in late August 1989, when Voyager 2 swept past Neptune at an altitude of just over 4,900 kilometers above the planet's North Pole clouds. That encounter was not just the last postcard from the planetary tour. It was also a gravitational slingshot that decided the fate of the entire remaining journey. To fly close enough to Neptune and scout its largest moon, Triton, the navigation engineers chose an approach trajectory from above the planet, and as a result, Neptune's own gravity bent Voyager 2 downward below the ecliptic plane, the plane that contains nearly all the planets of the solar system. From that moment, Voyager 2 was no longer flying the path that every other interplanetary spacecraft had taken. It gradually tilted southward away from the sky that radio dishes in the northern hemisphere of Earth could observe. And 34 years later, that seemingly harmless technical detail became the reason why in July 2023, only one single antenna on the entire planet was in the right position to save the silent machine at the edge of the solar system. That antenna is called DSS-43, a 70-meter radio dish located at NASA's Deep Space Communications Complex in Canberra, Australia. It is the only antenna in the southern hemisphere powerful enough and transmitting at the right frequency to talk to Voyager 2. If DSS-43 had been offline during that exact week, as had happened for 8 months in 2020 during antenna upgrades, there would have been no plan B. But the reason why Voyager 2 was worth saving to that extent is not in the 4 planets it visited. It lies in a small instrument that Voyager 2 carried on its journey south and out of the solar system. That instrument is called the Plasma Science Instrument, abbreviated as PLS. PLS was designed to directly measure the density, speed, and temperature of plasma particles in the environment around the spacecraft. Direct eyes looking at the material that makes up the solar wind and the space between the stars. Voyager 1 also once had a PLS like that. But in 2007, that instrument failed permanently. Since then, Voyager 1 could only measure plasma indirectly through plasma waves, like guessing the content of a conversation by listening to the bass through a wall. Voyager 2 still had its direct eyes. On the 5th of November 2018, 6 years after Voyager 1, Voyager 2 crossed the Heliopause, the outermost boundary of the solar system, where the solar wind finally runs out of energy and meets the pressure pushing in from the interstellar environment. But unlike its twin, which had crossed that boundary while blind Voyager 2 crossed it with its eyes still working, that made it the only machine in all of human history to have directly measured plasma density at the edge of the solar system. Not one of many, not the first machine. The only machine. And what those eyes saw at that boundary is still dividing the scientific community today over the most basic question, what is the real shape of our home? For many decades before any spacecraft could reach the edge of the solar system, scientists had built detailed mathematical models describing what the Heliopause would look like to a machine passing through it. Not guesses, but serious, peer-reviewed, rigorously tested models built by some of the best plasma physicists alive. And almost all of those models told the same story. The Heliopause would be a smooth, gradual transition zone spread out over many astronomical units, hundreds of millions of kilometers. Inside the solar wind would gradually thin out, temperature would gradually drop, particle density would gradually change. Outside the interstellar plasma would gradually become clearer, gradually denser. In between there would be a soft transition region, like where a river slowly flows into the sea, no sharp boundary, just a slow blending of the two environments. When Voyager 1 crossed that region on the 25th of August 2012, the data it returned basically matched this picture. The transition took place over many days. Plasma wave oscillations showed a slow, gradual process exactly as the models predicted. The story seemed closed. The edge of the solar system was a smooth transition river meets sea. 6 years later, on the 5th of November 2018, Voyager 2 crossed the same boundary, but this time not with ears inferring through waves, but with direct eyes looking at the plasma itself. And what those eyes recorded stunned the entire science team at the Johns Hopkins Applied Physics Laboratory. The transition did not take place over many days. It took place in just one day. The plasma density around Voyager 2 did not gradually change. It jumped 20 times in such a short time that the models had no place to explain it. That was not river meets sea. That was like stepping over a cliff. In the paper published in Nature Astronomy in November 2019, the research team led by Stimatios Krimigas and Ed Stone used words that scientific papers very rarely use. Sharp, cliff-like, unexpectedly steep. Two twin machines built at the same time, on the same assembly line, had crossed the same boundary only 6 years apart, and recorded two completely different things. One said the edge of the solar system is smooth like river meets sea. The other said the edge of the solar system is a cliff. And that cliff suggested something no model had ever accounted for. The edge of the solar system is not the fuzzy boundary the models had assumed for more than half a century. It has structure, it has angles, it has shape. The urgent question became, what is that shape? Now pause for a moment and let that question sink in. Over the past few centuries, humans have mapped everything we have touched. We have drawn the boundaries of every continent, measured the height of every mountain, the depth of every ocean trench. We have mapped the surface of Mars at 25-centimeter resolution. We know the shape of Pluto, of Bennu, of an asteroid only a few hundred meters wide, hundreds of millions of kilometers away. We have photographed hundreds of thousands of galaxies 13 billion light-years away, and know whether they are spiral or elliptical. But there is one map we have never drawn, the shape of our own home. Right now, the international plasma physics community is arguing between three competing models for the shape of the heliosphere: the classic spherical bubble model, the long-tailed comet model proposed by David McComas's team at Princeton, and the flattened croissant model developed by Merav Ofer's team at Boston University. You are living inside one of these three shapes right now. Your entire life has been lived inside a cosmic bubble that no one, not NASA, not ESA, not any physicist on this planet, can be certain of its shape. And that machine, that data, those senses, we almost lost all of it because of one mistyped command sequence. Let us go back to the night of the 1st of August, 2023. At NASA's Jet Propulsion Laboratory in Pasadena, California, the Voyager team had just received news that was half good, half worrying. After 11 days of scanning the sky with the giant radio dishes of the Deep Space Network, they had found a faint carrier wave, a heartbeat echoing back from 20 billion kilometers. Voyager 2 was still alive. It was still transmitting a signal. But its antenna was tilted 2 degrees away from Earth, and therefore even if it screamed anything, we could only hear a whisper that could not extract any scientific data. The heartbeat told them the machine was alive, but it did not tell them the machine could be saved. On the mission team's table was a backup plan that had been programmed into Voyager 2's software years earlier. Every few months, the machine would automatically perform an orientation reset, turning its antenna back toward Earth. The next reset was scheduled for the 15th of October 2023. If the team waited until then, Voyager 2 would heal itself and everything would return to normal. But waiting until the 15th of October meant 75 more days of silence. 75 days of lost scientific data, 75 days during which anything could happen to the 46-year-old machine drifting in the dark, a collision with cosmic dust, a sudden hardware failure, an electronic shock. For a spacecraft that had lived 9 times its designed lifetime, every week of waiting was a week betting its life on luck. The team did not want to wait. But the alternative was a technical gamble, to the point that even the project manager, Suzanne Dodd, one of the most veteran engineers still alive on the Deep Space Network, had to admit to the press there is a low probability this command will succeed. Because to save Voyager 2, without waiting until the 15th of October, the team would have to send a command that would make the machine turn its antenna back toward Earth. But that command had to reach an antenna that was tilted 2 degrees, not pointing correctly, only catching the edge of the most sensitive part of the receiver. The Hail Mary plan was named the Interstellar Shout. The team would use the DSS-43 antenna in Canberra to fire an S-band signal at 100,000 watts, the highest power the entire Deep Space Network could generate. They would time the shot precisely at the optimal moment in the tracking pass when the geometry between Earth and Voyager 2 gave the highest chance of being heard. 100,000 watts into the darkness, hoping 22 watts would answer. Odds of 4,545 to 1, like shouting into a sawmill to hear a whisper reply from 20 billion kilometers. And only once. No second chance. If the shout did not arrive at the exact moment the machine's antenna was in the right position, or if 100,000 watts was not enough to overcome the 2-degree tilt, there would be no other option except to wait until the 15th of October. The team fired the command on the 2nd of August, and then they waited 18.5 hours for the signal to travel from Canberra to Voyager 2, 18.5 hours for the reply, if there was one, to travel back to Earth, a total of 37 hours of waiting. 1 hour passed. Nothing. 12 hours passed. Nothing. 24 hours. 36 hours. The control room in Pasadena was packed. No one wanted to go home. Linda Spilker, the Voyager project scientist, described it, "We waited in the highest state of tension. It was all hands on deck." Suzanne Dodd, every night during that period, could only say briefly to the press, "You do not sleep well." At 12:29 a.m. Eastern Daylight Time on the 4th of August, 2023, 37 hours and 4 minutes after the command was sent, Voyager 2 began sending back scientific data. The machine had heard the shout. The antenna had turned back to the correct direction. Data was flowing to Earth as if nothing had happened. In an interview a few weeks later, Dodd described this twin machine with a phrase she had used many times over the decades of operating the mission, a spacecraft with 9 lives. It had just used another one. But saving Voyager 2 was only a small victory. Because what that machine had measured 5 years earlier at the edge of the solar system, we still do not fully understand the real meaning of it. Let's go back to November 5th, 2018. Voyager 2 was approaching the Heliopause at a speed of 15 kilometers per second. The only eyes in human history were looking straight at the edge of the solar system, wide open. The plasma cliff we just talked about, the sudden transition in just 1 day, that was only the first sign, the most superficial sign, that the old model was wrong. As scientists continued to analyze Voyager 2 data in the months that followed, 3 even bigger, stranger, and more unexplainable discoveries gradually emerged. 3 discoveries that each, if standing alone, would have been enough to rewrite a chapter in plasma physics textbooks. The first discovery, and perhaps the most uncomfortable for theorists, was about the magnetic field. For more than half a century, every model of the Heliopause had made a prediction that all physicists agreed on. Inside the bubble, the magnetic field would be the sun's magnetic field, generated and carried by the solar wind. Outside the bubble, the magnetic field would be the galaxy's magnetic field, a completely different electromagnetic field, created by physical processes hundreds of light years away. These 2 magnetic fields, according to every model, must have different directions. They were 2 separate environments, 2 separate stories. The boundary between them had to be a sharp jump in magnetic direction. Voyager 2 measured the opposite. The 2 magnetic fields on either side of the Heliopause did not point in different directions. They were aligned with each other. Same direction, almost identical, as if some mysterious mechanism was locking them together at the boundary. To this day, in 2026, 8 years after this data was recorded, no model has satisfactorily explained why. The second discovery was even more uncomfortable. As Voyager 2 passed through the transition region, its eyes detected something that no model had room for. An intermediate plasma layer, not the plasma of the inner heliosheath, not the plasma of the interstellar space outside, but a third region with completely different characteristics, a kind of buffer layer between the 2 environments that no one knew existed before. No model predicted it. No model could explain where it came from. It was simply there, clearly recorded by Voyager 2, and now sits on the scientific community's table like a puzzle piece that does not fit any picture. The third discovery is perhaps the strangest of the 3. The Heliosphere bubble, according to every classical model, had to be a closed structure. Solar wind pushing out from inside, interstellar plasma pushing in from outside, and at the Heliopause, these 2 pushing forces meet to create a boundary that does not allow matter to pass through. Voyager 2 discovered that the bubble was not closed. plasma from the interstellar environment was leaking back into the heliosphere. Not much, but enough to detect. Enough to prove that the edge of our home was not a wall, it was a permeable membrane. When these three discoveries are placed side by side, a new picture begins to emerge. The Heliopause is not the clear boundary as models had assumed for more than half a century. It is a negotiation zone, an area where the solar system and the galaxy are exchanging magnetic fields and plasma in ways we are only beginning to see. And each of these discoveries takes the scientific community one step further away from consensus on the shape of our home. The debate about that shape is not closing, it is opening wider than ever. And now, as Voyager 2 is losing its senses one by one, that debate is racing against time. And this is the part that makes this story much more heartbreaking than it appears. The three discoveries we just talked about all rely on data from the only eyes Voyager 2 had at the edge of the solar system. Those eyes, the sensor box named PLS, permanently stopped working on September 26, 2024. Not because it broke, not because cosmic radiation finally destroyed some component. It was turned off because Voyager 2 no longer had enough power to keep it running. 6 months later, in March 2025, it was the turn of the low-energy charged particles instrument to be shut down. Same reason. Not enough power. Voyager 2 draws power from 3 radioisotope thermoelectric generators, basically 3 containers of plutonium-238 that generate heat as they decay. When the machine was launched in 1977, they produced 470 watts of electricity. 48 years later, only about 250 watts remain. Each year, they lose another 4 watts. At this rate, by the early 2030s, Voyager 2 will fall silent forever. The mission team made a list, which instrument to shut down first, which later. PLS lost in 2024, LECP lost in 2025. By the end of 2026, in the coming months, the cosmic ray subsystem will be next to be shut down. After CRS is shut down, Voyager 2 will have only 2 instruments left operating, the magnetometer and the plasma wave system, exactly the same number as Voyager 1. Scientifically, that is the moment Voyager 2 officially ceases to be a special witness. It becomes an ordinary machine like its twin. Meanwhile, from May to June 2026, NASA engineers conducted a daring experiment with the internal name Big Bang Procedure, an effort to reallocate power to squeeze more capacity from components operating below performance. This approach carried such high risk that the team decided to test it on Voyager 2 first, because Voyager 2 is closer to Earth. There is a cold irony in that choice. Voyager 2, the machine that measured the 3 most valuable discoveries in the entire Heliopause story, was chosen as the guinea pig for its twin. If Big Bang failed, the result could be the loss of the machine that raised the biggest question it had not yet seen answered. And while Voyager 2 is losing its voice, a new machine is flying toward a special observation point to answer exactly the question Voyager 2 raised. That machine has a name, and there is a date on the calendar when it will say something about the shape of our home, a date that has been locked in. That machine is called IMAP, short for Interstellar Mapping and Acceleration Probe. It was launched on September 24, 2025 from the Kennedy Space Center on a SpaceX Falcon 9 rocket. After 3.5 months of flying on a precisely calculated orbit, it reached its destination on January 10, 2026, the Lagrange 1 point, a special position about 1 million miles from Earth toward the Sun, where the gravitational pull of the Sun and Earth balance each other so a spacecraft can park and observe stably. On February 1, 2026, IMAP officially began its scientific mission. On board, it carries 10 instruments, specially designed to answer the question Voyager 2 left on the table. Among them, the instrument the heliophysics community has been waiting for more than a decade is called IMAP Ultra, capable of measuring neutral atoms with energies up to 100 kiloelectron volts. The range that theorists had calculated years earlier would be enough to distinguish between 3 competing models after 17 years of debate. David McComas, Princeton professor and IMAP principal investigator, said about the first few weeks of operation, "It is astonishing that in just the first few weeks of observation, we saw clear and consistent ENA data by a factor of 10,000 in energy. In the period from 2026 to 2027, right now and for the next approximately 18 months, IMAP is expected to provide the first experimental evidence that can distinguish between the sphere, the comet, and the croissant. The answer to the question Voyager 2 raised 8 years ago is coming. But there is a cold irony. When IMAP delivers the final answer, Voyager 2 may no longer have any instruments operating. IMAP will speak the answer for an older brother that has gone silent. But even when IMAP has given the final answer, there is one thing on Voyager 2 that will still be moving, and that thing will reach a star that humans will never touch. Screwed to the frame of the 22-watt machine drifting in the darkness is a gold-plated copper disc 30 centimeters in diameter, designed to last longer than anything humans have ever built. That disc is called the Golden Record. It contains 55 greetings in different languages, 90 minutes of music from Bach to Peruvian folk music, the sound of ocean waves, rain falling on a forest, the heartbeat of a woman, and the laughter of a child. There is one detail very few people have noticed. Because Voyager 2 launched 16 days before Voyager 1, the first golden record to leave Earth was the one on Voyager 2. If that golden record is truly humanity's message in a bottle thrown into the cosmic ocean, then the first bottle belongs to the machine that nearly got lost in 12 days of silence in 2023, the machine that measured the cliff and the 3 discoveries at the edge of the solar system. In about 40,000 years, Voyager 2 will pass near a red dwarf star named Ross 248, about 1.7 light years away from us. Ross 248 has no known planetary system, no one to listen. But Voyager 2 will get there, carrying human laughter and 55 greetings in languages that by then probably no one on Earth will still speak. Meanwhile, Voyager 1 flies in a completely different direction toward Gliese 445. 2 twins, launched 16 days apart, will separate in the eternal darkness and never meet again. When Voyager 2 finally approaches Ross 248, the question about the shape of our home will probably have been resolved long ago. Textbooks will write it definitively. But while humans are confidently turning those pages, the machine that raised that question is still flying silently, carrying an old picture, an outdated map, and the laughter of people who are no longer here. Now let's go back to science, and to the specific question that Voyager 2 left on the table. Voyager 2 has given us 3 discoveries: aligned magnetic fields, plasma buffer layer, reverse leakage, but this is something very few science videos dare to admit straightforwardly. Those 3 discoveries are not enough to settle the answer. They are compatible with many different models. 3 models are truly competing on the table of the scientific community in 2026. The first model is the classic spherical bubble. Simple, symmetrical, no nose, no tail. The problem is it does not match almost any data. Both Voyager and the IBEX satellite show the Heliosphere has a clear nose. The spherical model has almost been eliminated. The second model is the comet with a long tail, proposed by David McComas's group at Princeton based on IBEX data, an egg with a short nose in front and a tail stretching thousands of astronomical units behind. It is compatible with part of the Voyager 2 data, but faces serious difficulties when trying to explain the plasma buffer layer. The third model is the flattened croissant, developed by Merav Ofer's group at Boston University. No long tail, instead 2 lobes like 2 short jets. The study by Zhang and colleagues published in the Astrophysical Journal Letters in December 2024 leans toward this model, but leans toward is not settles it, and this is the most ironic detail. It was McComas himself, the head of the Comet Group and the principal investigator of IMAP, who will provide the final answer, who stated in Planetary Radio in January 2026, "Personally, I do not think the shape of the heliosphere is really a big issue." The person about to settle the answer down plays the very question that the community has debated for 17 years. There is one more mystery. In 2009, the IBEX satellite discovered a band of energetic neutral atoms draped across the front of the heliosphere, the IBEX ribbon. 17 years later, no one has explained why it exists. And this is the most ironic blind spot. Both Voyagers have flown on both sides of the IBEX ribbon. Neither went through it. The only eyes we had at the boundary missed the very biggest mystery of that boundary. A dying machine is a witness losing its senses, and that witness from the beginning could not look at the hardest spot. Humanity has mapped Mars with 25 centimeter resolution, has measured the mass of subatomic particles, has calculated the age of the universe with an error less than 1%. But we cannot answer what shape our home is, and there is a hard-to-swallow truth at the center of all this. The hard-to-swallow truth is this. The question that Voyager 2 raised at the edge of the solar system may not be answered in the lifetime of most people watching this video. Not because science does not care, but because right now, in 2026, there is no mission flying that is capable of measuring the direct edge of the solar system, and there will not be any such mission for many decades to come. IMAP is sitting at the Lagrange 1 point, about 120 astronomical units away from the edge. It does not measure directly, it measures indirectly, collecting energetic neutral atoms flying back from the edge, like standing at one end of the house and trying to imagine the room at the other end by listening to echoes through the wall. David McComas himself admitted that current MHD models cannot settle the shape out to 400 astronomical units. There is a real possibility that IMAP will provide the most detailed map that humanity has ever had, but still not enough to settle the question. New Horizons just woke up on June 23, 2026, after 321 days in hibernation, and is heading toward the termination shock around 2028 to 2029, but it does not carry PLS. It will touch the edge with the eyes of Voyager 1, not Voyager 2. The Johns Hopkins Interstellar Probe, if funded today and launched in 2036, will reach the edge around 2051, 27 years after Voyager 2's PLS was shut down. Currently, it has not been funded. By the end of 2026, Voyager 2 will lose the cosmic ray subsystem. In the early 2030s, both Voyagers will run out of power. During that time period, humanity will continue to live in a home whose shape we do not know. We will have models, we will have debates, but we will not have the final answer. This is what I want you to take away from all this. This is what I want you to take away from all this. We are the species that has mapped the ocean floor, has measured the height of every mountain on Earth, has photographed galaxies 13 billion light years away, has calculated the exact mass of subatomic particles that the naked eye can never see. But there is one simple question that seems almost ridiculous, which humanity still cannot answer. What shape is our home? Not Earth. We know Earth. But the cosmic home, the solar wind bubble surrounding every planet, every spacecraft we have ever launched, and every living creature that has ever existed. Is it a sphere? A comet? A croissant? We do not know. We have lived 4.5 billion years inside that shape. Human civilization has existed 5,000 years inside that shape, and we have not once in the entire history of human knowledge seen it from the outside. The only machine that has come closest to doing that is losing its senses. There is a historic moment passing as we read these lines. A 22-watt machine is losing parts of itself one by one, and all that humanity can do at this moment is wait. Wait for IMAP to tell us what Voyager 2 almost finished saying. Wait for our home to finally have a map. And while waiting, remember that there is a humility that only those who live at the edge of knowledge can understand, that we do not yet know the shape of our own home. If this kind of story is what you came here for, subscribe right now and turn on notifications. Leave a comment and let me know what you think the solar system looks like and why. This story is still long. We will return to the edge when IMAP has its first results.